Okay, in the previous lecture I showed you how to do what's called a definite integral, which tells you the area under the graph of a function, right? So let's look at this picture. Here's a function, f of x equals 4x minus x squared. And it's graphed here in the picture for us. Okay, and the question is, what is this area under here? So you already know how to do this from the last lecture. We write the integral of 4x minus x squared with respect to x from 0 to 4. And how do we do that? We anti-differentiate. So the antiderivative of 4x is, do you remember how this goes? It's 4 times the x becomes squared, and we divide by 2. Remember that? And then we have minus, and then for x squared, the x becomes cubed, and we divide by 3. And what's 4 over 2 is 2, right? So let's write that. And then we evaluate that from 0 to 4. So that means 2 times 4 squared minus 1/3 times 4 cubed minus 2 times 0 squared minus 1/3 times 0 cubed. And that equals, now there's just a little bit of arithmetic involved here. You can all work that out. It's going to come out to be 32/3. Okay, minus, and this one's obviously 0. And so our answer is 32/3. This is all from the previous lecture. That's the area under the curve, 32/3 of a square unit. Okay, now what I want to show you this time is what is really going on behind the scenes. Okay, and this is going to be very tedious. We're only going to go through it once. You need to see it so that you understand what's going on behind the scenes. Okay, so here's what we do. We take the x-axis and we divide it up into intervals. Okay, and so in this picture that you're seeing right there, we have divided it into 4 intervals. One right there, one right there, one right there, and one right there. Okay, we can estimate the blue area using rectangles. It's not a very good estimate, but nonetheless, we can estimate it. Okay, look at this rectangle right here. What they've done is they've made a rectangle whose height is the height of the function at the right-hand side of the rectangle. So in other words, they took this interval right here from 0 to 1. And the right side of that is right here at 1. You plug 1 into the function. Remember, this function is 4x minus x squared. Okay? So what is, that's f of x. What's f of 1? F of 1 is 4 minus 1, which is 3. And so that's why this rectangle has a height of 3. Okay? And what's the width? The width is 1. The height is 3. So what's the area of that rectangle? Height times width. The area is 3. Okay, and that's what this 3 is right there. That's the area of that rectangle. Now let's go to the next rectangle. Okay, the right hand end point is a 2. What is f of 2? F of 2 is 8 minus 4, which is 4. Okay, so the width of this rectangle is 1, and the height is 4. Height times width is 4 times 1, so that has an area of 4. And that's what that 4 is right there. Okay, that's this rectangle. Has an area of 4. Okay, let's go to the next rectangle. The width is 1. What's the height? The right hand end point is a 3. F of 3 is 12 times 9, which is 3. So for this rectangle right here, the width is 1, the height is 3, the area is height times width, which is 3 times 1, which is 3. Okay, and then let's go to the last rectangle, which you don't even actually hardly see. You can barely see there. The width is 1, but what's the height? The right hand end point is a 4. F of 4 is 16 minus 16, which is 0. So the height of that rectangle is 0. So the area is height times width. 0 times 1, the area is 0. Okay, and now you add those 4 rectangles up, and we get 3 plus 4 plus 3 plus 0, which is 13. Now, is that the same amount of area as shaded in blue? No, it's not, right? But it is an approximation. What I mean by that is look at the blue shaded area. It's a parabola, right? It's a parabolic area, okay? Now, sort of let your eyes focus on the red rectangles. It's not a very good approximation, but do you see that the red rectangles form something of a parabolic shape? Not exactly, but kind of, right? It's kind of like looking at a really, really old, like 8-bit video game where they tried to draw a parabola, but because everything is pixelated so much, the parabola looks very blocky. Okay, so we could say the area, in this case, I'll just put A for area, is approximately 13. Okay, not a very good approximation, but it is an approximation. Now, how could we make it a better approximation? How about if we increase the number of rectangles that we use? Now I think you'll agree that those rectangles are forming a parabolic type shape. It doesn't match up perfectly with the blue parabola, but it's a heck of a lot closer than the first example, isn't it? And so if you were to add up the areas of all of these rectangles, it would give you an answer that is close to the blue area. Okay, do you see how that's working? So, how could you get a perfect answer? Well, the idea is this. You keep doing these estimates with more and more rectangles. Okay? Let's call the number of rectangles n. Okay, I'm going to erase this calculation here. Okay, let's erase some of this writing that I drew in the picture. Okay, So let's use n for the number of rectangles. I'm just going to write n equals number of rectangles. Okay. And let's write, so by the way, we can go ahead and say in this first picture then n equals 4, right? In the second picture, oh, by the way, I know when you look at that, you might say, oh, there's only 3 rectangles, but remember there's that fourth rectangle with the height of 0, okay? In the second picture, n equals, well, we would have to count there. Let's see what it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 rectangles. Okay? All right. Let's put x sub I as the right-hand endpoint of the ith interval. Okay, so what do I mean? Let's draw it in these pictures. Okay, so in the top picture, 1 is x1, 2 is x2, 3 is x3, and 4 is x4. Okay? Let's look at the bottom picture. Here's x1 right here. What number would that be? Well, the whole picture goes from 0 to 4, and we've divided that up into 16 intervals. So when you take when you take 4 and divide it up into 16 pieces, how long is each piece? 4 divided by 16 is 1/4. So x1 would be 1/4. Okay? Here's x2. That would be 2/4, or 1/2. Here's x3. That would be 3/4. Here's x4 would be 4/4 or 1. You see how that works? And you would get all the way here to the last one would be x16. Would be the number 4. Okay? All right, now you form those rectangles. What is the width of each rectangle? Let's figure that out. Let's figure this out. Okay? So you have the interval from 0 to 4. And you divide that up into n rectangles. Then how wide will each rectangle be? So think of it. Think about it. The width of the whole picture is a width of 4, right? From 0 to 4. And we're dividing that up into n rectangles. Then the width of each rectangle would be 4 divided by n. Does that make sense? So in the top picture, we divided into 4 rectangles. So each rectangle had a width of 1. Okay. In the bottom picture, they have divided into 16 rectangles. So let's zoom in there. So each rectangle would have a width of 4 over 16, which is 1/4. Okay? The whole picture has a width of 4, 0 to 4, and you divide that into n rectangles, then each rectangle will be a width of 4 divided by n. Okay, now let's find the height of each rectangle. Okay, so we're using the right-hand rule, which means the height of each rectangle is calculated by plugging the right-hand endpoint into the function, and you get the height. Okay, well, that one should have gone up to there. All right, that's why it's called the right-hand rule, because we're plugging in the right-hand endpoint. Some people choose to use the left-hand endpoint instead. Some people choose to use the midpoint right in the middle of the rectangle. But we're keeping it the easiest way possible, and we're using the right-hand endpoint. Okay, what have I called the right-hand endpoint? Look, I've called it x sub I. So the height of each rectangle is f of x sub I. Okay? Now, I bet we could calculate. Well, let's not calculate it yet. I think we can calculate exactly what each x sub I equals, but let's wait a minute, okay? Okay, so what would be the area of each rectangle? Well, area is height times width. So it would be f of xi times 4 over n. Okay? Now, how do we get an approximation of the blue area? We add up all of the rectangles, right? So in other words, the integral of f of x from 0 to 4 in this case is approximately equal to f of x1 times 4 over n, that's the area of the first rectangle, plus f of x2 times 4 over n, that's the area of the second rectangle, plus, and then we continue until we run out of rectangles, right? So where will it stop? It stops when you get to f of xn times 4 over n. Okay? Now, there's a shorthand way of writing that. You use capital sigma, the Greek letter, capital sigma. It's their version of a capital S. Okay, and that means sum. And we're doing f of xi times 4 over n, and I starts at 1 and then goes up to n. So you write down here I equals 1, that means I is starting at 1, and then up here you write an n, that means I is stopping when it gets to n. Okay? So I'm going to actually write that up here instead of writing all of those out. Let's just take this and just slide it right up there. Okay, now see, that's just an approximation, right? None of those pictures, there's only two pictures over there, but neither one of them is going to give us the exact blue area, is it? But you can see from those two pictures that the more rectangles you use, the smaller they are, and the better they conform to the parabola. So, how many rectangles do you have? We've called that number n. So the bigger n is, the better the rectangles will conform to the parabola. And so the better of an estimate we will get for the area. Is it possible to make that answer perfect instead of just an estimate? Well, maybe not in reality, but in theory it is possible. I would just say use infinitely many rectangles, and then they will be so narrow that they will fit the parabola perfectly. Well, can you really use infinitely many rectangles? Again, not in reality, but in theory you can. We would just do this. Let me bump this over, and let me just throw in here at the beginning to do the limit. That's not very nice. Not very neat. Let me do better. The limit as n goes to infinity. And then instead of an approximate answer, we will get an exact answer. Okay? Let's work this out and see if we get the correct answer. So we would have the limit as n goes to infinity of the sum I goes from 1 to n f of, now we'll need to figure out what number goes right there. But once I figure that out, I will plug it into f, and then I will multiply times 4 over n. Okay, so let's figure out that number that goes in the parentheses. It's x sub I, which means the right-hand endpoint of the ith interval, right? So the first one would be 4 over n. The second one would be 4 over n plus 4 over n, which is 8 over n. I should write these down maybe. Let's keep track of these in writing. Okay, so the first one is always going to be 4 over n. The second one will be 4 over n plus another 4 over n, which is 8 over n. The third one would be 4 over n plus 4 over n plus another 4 over n, which is 12 over n. Do you see a pattern there? Don't you agree that the ith rectangle stops when you get to 4 over n times I, right? So that's x sub I is 4 over n times I. By the way, I here is not an imaginary number, okay? It's just a letter that I'm using to count the intervals. That's why they use I. I is short for interval. Okay? So this is what I want you to get right here. X sub I equals 4 over n times I. So right there where it's underlined in pink, I need to take 4 over n times I and plug it into f. Okay? And now we're just going to do a bunch of algebra. In fact, all of this is really just basic high school geometry and a bunch of algebra. Okay? So we have the limit as n goes to infinity of the sum where I goes from 1 to n. Now, what is this going to equal? I'm taking 4 over n times I and I'm plugging it into f. Up here is our function f, in case you forgot. So what are we going to get? We're going to get 4 times 4 over n times I minus 4 over n times I squared, right? And then that is being multiplied times 4 over n. Okay, let's work that out. Okay, like I said, this is all just going to be a whole bunch of algebra, that's all. So let's work that out. This will be 16 times I over n minus 16 times I squared over n squared, and then that is multiplied times 4 over n. Let's go ahead and distribute the 4 over n. So that'll give us 64I over n squared minus 64I squared over n cubed. Okay. Now, I would like to separate out those i's. Let me show you how I'm going to do it. I'm going to write these down, steps down, so that you can see. Okay, so let's start by just, you see how I wrote the i's in the tops of the fractions? Let's start by pulling them out of the fraction and write like this. Okay, I think that'll be easier to follow. And I'll make the brackets into parentheses here, I think. Okay, all right. Now, I can do this. I can write 64 over n squared times the sum of a bunch of i's. You see, because the 64 over n squared can be separated away from the I, and basically what I did was I factored it out front. Okay, and then I'm going to have minus 64 over n cubed times the sum of a bunch of I squareds. And then we're going to do the limit of all of that as n goes to infinity. Okay. Now there's a formula for each of these. I don't know if you know the formula or not. I meant to write it down first before we even started, and I forgot. So I'm going to write it down for you right now, okay? And you don't need to know these, and I don't expect you to know them. These are, this is information that I'm giving you, okay? The sum of a bunch of i's, where I goes from 1 to n, that would be 1 plus 2 plus etc. plus n. There's a formula for that. Maybe you've seen it before and maybe you haven't. It's n times n plus 1 over 2. Okay? So again, I'm not assuming that you would know that. That's information I'm giving you, okay? Because we're going to use that information to simplify our problem. And there's also a formula for the sum of a bunch of squares. So this would be 1 squared plus 2 squared, etc., up to n squared. It's a much more complicated formula. This one is n times n plus 1 times 2n plus 1 over 6. Okay, so if I gave you those two formulas to use, then you could plug them into our problem over there, couldn't you? And then it would make the problem start to become a lot easier. We would have the limit of 64 over n squared times n times n plus 1 over 2 minus 64 over n cubed times n times n plus 1 times 2n plus 1 over 6. Okay? Let's just continue working that out. I know there's a lot of steps to this, and that's why it's good that we don't actually have to do the problem this way. Okay, so let's see what we have here. So this stuff here, if you multiply that out, we're going to get 64n squared plus 64n over 2n squared and those two multiplied together, that's going to give us 128 n cubed plus 192 n squared plus 64n over 6n cubed. I just multiplied them out is all. I didn't do it in my head. I had it written down beforehand. You would get the same answer if you multiplied them out. Okay, let's reduce those fractions. So the first one, I can factor out an n from the top and the bottom, and also a 2, and that fraction would reduce to 32n plus 32 over n. The second fraction, I can factor out an n from the top and bottom, and I can factor out a 2 from the top and bottom, and you would get 64n squared plus 96n plus 32 over 3n squared. Okay, now I would like to do this subtraction right there, so I need a common denominator. So let's rewrite the first fraction so that its denominator will match the second fraction. We do not need to change then the second fraction. Okay, so what do I have to multiply by? I need to multiply by 3n, right? So the top will become 96n squared plus 96n. Now I can do the subtraction. Oops. Subtract the second fraction from the first, and you're going to get 32n squared plus 32 over 3n squared. And everything up until this point, let's see if we can see everything. Everything from here down to here has just been algebra. Okay? There's only one tiny step of calculus at the end, and that is to do the limit. But look at what we have here. This is an easy limit, isn't it? It's really easy. You know how to do this already. We've already covered it. The top is degree 2. The bottom is degree 2. So the answer will be right here, 32/3. I'll show you again in case you forgot how we do that. What we do is we divide everything by n squared, and then it will look like this. And then you let n go to infinity. You get 32 plus 0 over 3, and our answer is 32/3. So let's shrink this down so we can see again. I know you can't read it anymore, it's so small. That's okay, you don't have to read it. I'm going to point out to you that 32/3 is how much area is right there. Okay? That's what's happening behind the scenes when you do an integral. Do you really need to do all of that yourself? No, you don't do any of that. You'd be crazy. Because why? Because there's a heck of a lot easier way to do it. What's the easier way? Well, here it is right here. We've already covered it. That's the easy way right there. You use antiderivatives instead. Okay? Why do antiderivatives give you the same answer? Well, that's something that I haven't shown you yet. So you would not know that unless you've taken this class before. Okay, I want to make that very clear. So you know two ways to do an integral. Okay? One way is this, which is use antiderivatives. Okay, get an answer of 32/3. Another way to do it is this, which is called a Riemann sum. Because it's a sum, remember that's what the sigma stands for, and because the first person to figure this out was named Bernard Riemann. So it's called a Riemann sum. And that also gives us an answer of 32/3. Same answer. You can use antiderivatives, or you can use Riemann sums. Which one would you use? I hope you would use antiderivatives. Look, just compare the amount of work that's involved. So why do I even bother showing you how to use Riemann sums when nobody in their right mind would really do the problem that way? The reason I showed it to you is because, and here's what's really important, I want you to understand that when you use antiderivatives and you do the problem this way, up here, okay, I want you to understand that the math is doing all of this behind the scenes. You don't have to do all that Riemann sum business, but that's what's really happening behind the scenes when you do the antiderivative stuff. Okay? And you should have an idea of what's going on behind the scenes when you do stuff. Even if you don't do those calculations yourself, because there's a much easier way, you should still at least have an idea that that's what's really happening behind the scenes. Okay? Now, the only question that's left to answer is, why in the world does the answer, when you use antiderivatives, come out to be the same answer that would happen if you use Riemann sums? Because this is definitely the correct answer. The Riemann sums will definitely give you the correct answer, because you can see in the pictures how the areas of the rectangles conform to the shaded blue area. So we know that the Riemann sums will give us the correct answer. The question is, why do the antiderivatives give us the correct answer as well? That's the big question, and we'll answer that in the next lecture.